So good morning, everybody. I've had the privilege of knowing Kristen for quite a while, but some of you maybe not for so long. So let me just say a few words and thank him for giving this talk that he's going to give this morning. Kristen is a very versatile physicist. If you look at what he's been doing over his career, it's very varied. Accretion disks near and far. When the hot Jupiters came out, he jumped on them. We heard about some of that last week. Aunt Reese, he's worked on, we heard about that yesterday. Atmospheric circulation in planets, which planets are habitable, and why not. When planetary systems form, how do they go unstable, etc., etc. So he's a very versatile trailblazer, I would say. And in the last little while, including the crescendo in the last year, he's pivoted what he's working on once again, and that is in the direction of AI, and that's what he's going to tell us about today.
Great, thank you, Peter. Thank you for the invitation. I didn't realize when I said yes that it would be an hour or 50 minutes, so that forced me to organize my thoughts and sort of justify more why I'm doing this. So it's a provocative title. But my goal with this is to see if some of you at least come out of it thinking, well, maybe there is something to this. The notion that eventually we might get an AI physicist, maybe this is not falling to the hype about AI, and maybe it's worth thinking about it more seriously. Okay, that's a goal. And I just lay out the landscape for you as I see it, and then we can talk about at the end of the talk. This is a okay. So what's going on here? I cannot change my slide. One second. Okay, here we go. Okay. So this is a kind of the talk. I'm gonna just make clear that I only care about artificial general intelligence and just give you an example of what I mean. I'm going to tell you about the manifold hypothesis, which turns out is something that's not discussed so much in AI research, or if you just go and try to learn, you have to dig out to find this, but it's a motivator for all of deep learning, in my opinion, and it's actually one of the things that motivates me to go in that area, so basically, and I draw parallel to actually learning physics, so we'll see how that goes. I'll tell you briefly about the scaling hypothesis, so that's what's driving the race right now to building more intelligent machines. I'll tell you briefly about some frontier capabilities in case you have not been following. Just following the progress is very time consuming. And so I actually do that, instead of doing that. So I'll give you some sense of where I see things and how it's relevant to building an AI physicist. I'll give you some sense of what I'm thinking about. Evaluating the AI physicist is going to be important. I expect that as things go, and if they keep going the way they're going, eventually us physicists will be asked to evaluate some of these machines, right? I think some of them might be coming soon, actually, sooner than later. And then another thing is, why would you build an AI physicist? So I'm going to say a few words about what we might learn from an AI physicist, and is that interesting, and then conclude. So that's it now. Now I want to start with this. I'm teaching the Astro grad student what I call AI Essentials, which covers some of what is in this talk, and I start with that video. I like it because I think it resonates with people. So in case you don't know, because it's possible you don't know, this is a demo from OpenAI of a model that is not public yet. It's called Sora, and it has impressed people. I think it's maybe 6 months ago now, because it's text to video. So you say a brief prompt, like a bunny dancing, whatever. I don't know what the prompt is. So we can find them, okay? And then it produces short video like this. And what was striking to people is the degree of realism of these videos, okay? I'm reading that they are refining that model and they have plans to making it public. Okay, so why am I showing you this? Because there's two reactions to this video. You are a movie producer, say, and you're like, ooh, I need to change my business. I'm going to lose my business. Like, it's going to be able to create movies, you know, soon. And then the way I'm doing it, and it's basically very costly to have this movie production and this, all there is in that business, I need to adapt. So you're scared about losing your job and all this, which a lot of people feel about. It's a normal reaction. And so that's one way of looking at this. Like, this actually is creating movies. You see a defect here, by the way. You see, it's not far from perfect, but there is a ball that's coming and going through. I think that's a video hallucination, okay? And so that's one reaction. But the one that I would like you to think, reflect on, and just present to you is looking at this as a physicist. So there is one specific video I want to focus on. So I'm going to just go, because there is a lot there, you can find them online, okay? This is the puppies playing in the snow, you see? Let's look at the puppies playing in the snow. Okay, so I don't know who the prompt was, you could find it. And they're playing in the snow, and this is a pretty good video. So you look at it, it's like it's pretty realistic. So let me stop this. Oh, let me go back. As a physicist, I would like you to think about the following. When I see these puppies playing in the snow, is it just that that model, so I'm going to make a guess here. That model probably has been trained on all YouTube videos and more. I don't know, but like it's very likely. And so when that model is asked to do the puppies in the snow thing, these 3 puppies playing in the snow, does it actually essentially look for something it was learned, its memory, and reproduce it? Or is it that it has learned the laws of Newtonian mechanics and material properties of snow, and is actually simulating that in that video? Nobody knows. As of today, this thing is going like this, and nobody knows. If you look at the blog on OpenAI, they say we see evidence of physics learning. Okay? So this is where it gets interesting, because if you are minded into actually getting this area, you could go and say, when Sora is out, give me access to it, I want to test the physics of that thing. You could design prompts and go after, I'm going to test you on physics, generate videos that are physics testing, and I'd like to know what you know. Nobody's been doing that, as far as I know.
On what basis do they say that it's not physics?
There are various things here, but the permanence of objects is one of this, which is one of the things that the kids learn. There's various things that you should look at the blog, yeah. I'm going to just not talk about this at all. I just want to just try to resist that. You can passively look at videos and be entertained, or you can ask yourself, what is this thing really learning? And so that's really sort of the theme of this presentation. We should maybe start thinking about what is it that is really learning, and is it interesting to us as physicists? Okay, so then you might say, well, I'm sure there's a lot of puppies playing in the snow on YouTube. I haven't checked, but I'm sure that's true, right? So then, how about this one? I did go and check. Elephants made of leaves. And there are kids on a 2D page putting leaves and making an elephant. I couldn't find any videos like this. So then the question is what is it doing? It's somehow able to do the texture of leaves and the motions of leaves are sort of realistic and all this. Is it actually learning the physics of this? How to do that? Because there is no example on YouTube that I could find. I don't know that there is any video that is but the one generated by Sora, right? So this is what I'm challenging you here with, is like, maybe this thing is learning something that's really interesting, okay? And then I mostly will not talk about video. I can talk about it in the question session. I will talk about language models. Okay, so the first point I want to make is that I care about, sorry, there's this big thing on my screen that bothers me. Let me see if I can read it. I cannot see my, one second. Reduce that, okay. Okay, so what do I mean by narrow and general AI? Narrow AI, I took an example so that nobody gets offended from my own work, which is with the students and postdocs from here, years ago. You take digital elevation map of the moon, you build a deep learning, it's called a UNet structure, and then you get that to learn the masks of the craters, and once you have learned on a training set, you go and it finds new craters on the moon. Okay, so that was our paper. It's actually well cited. But I'd say if you present it with square craters on the moon, which I can probably cook up, is going to fail miserably. That's the meaning of narrow AI. It's very good at a very narrow task, and it is not like animals and us humans, we are very good at many different tasks. Okay, so what people are after now And I'd say a lot of people in astrophysics and physics, they're doing narrow AI. This is not judgmental. There's wonderful results coming out of it. It's great. There's a lot of things to be done there. My talk is not going to be about that. My talk is going to be about the general intelligence. So what I'm going to call AGI. This is a longer term in the press, so I'm not meaning things that are going to replace humans at work, whatever. I just mean a machine that can do many things, okay, in terms of tasks. And this has become a reality through these foundation models. It has become possible to train this machine on internet scale data due to some technical developments. And so as a result, then you can specialize them to do a lot of things. Especially they were specialized to be chatbots, because it's nice to converse to human. And that's how all this exploded. Okay? But that's just a specialized task that they have. They can do many other things in principle. Everything that's represented in the data, if they learn it well. Okay, so now let's talk about this. I think this is maybe the key motivator for why I'm here, and so I'd like to take the time to go through a few slides on this to see how you feel about it as physicists. There is a wiki page on the manifold hypothesis, but again, there is not a huge amount of work on it either. It's sort of a hypothesis that's out there. I think it makes sense. There is no theorem, there is no proof of it. Like a lot of things in AI and deep learning, there is limited things you can do with mathematical proof. We tend to lack that as physicists. If you go in that area, you have to just, okay, there is no proof, I'm going to work with what there is. It's kind of the way it goes. And he says the following. Many high-dimensional data sets from the real world actually lie on low-dimensional manifolds that are embedded in that high-dimensional space. So that's an abstract statement. I'll give you an example of an example interpretation of that. Images, natural images. Let's say that it's actually a square, but let's say it's because I picked that from a paper for convenience. Let's say this is 728 by 1280 image, and I have RGB 3-color. I'm doing the digital version of the argument here, but our eyes have color resolution, we have spatial resolution, so it actually does apply even to us as humans to some extent. Yeah, I think it doesn't matter. The digital version is easier for the argument, for the sake of argument. This is a nice national park that is meant to represent the sort of objects, colors, structures, textures that we find in the real world. And the argument is the following. If I count all the possible pixel combination of every single color here, I'm going to multiply these three numbers, and I'm going to get many, many millions of possibilities. And the argument is, if I take all of the natural image of the world, it will only need a subset of all these pixel possibilities. Therefore, the real world in that high-dimensional space maps onto a low-dimensional manifold. I think it makes a lot of sense. There is no proof of it, but intuitively, so that argument, I think you can object to it. But this is sort of the idea. And so, for us physicists, so if you are a pure AI person, you might think there's a data generating process, you don't care where it comes from, it's just statistically sort of generate things. For us, it's the physics that's the data generating process, so that's the distinction between the two approaches. But the manifold hypothesis applies as something that's worth thinking about. Let me just say one more thing here, because I'm going to come back to that. Language. Language is a sequence of letters from the alphabet and signs, space, signs, whatever, okay? Of all possible combination of sequences from my not vocabulary, but from my alphabet and signs, clearly, English language is also a low-dimensional realization of all possibilities. So language is also a low-dimensional manifold in that sense of a sequence, okay? So everything that we know in the world and we have learned as human is, I'm convinced, is probably a low-dimensional subset or subspace of all possibilities. And we as physicists have learned, we have humans as learned, as kids and growing up over there, but we as physicists, we have learned particularly insightful view on that manifold. That's what I want to push.
I just wanted to say, isn't that the same thing as saying that file compression is possible?
Yeah, it is related to compression. I'll get to that. Yeah. So I'm just going to show you one structure, one architecture from deep learning that I think actually illustrates a lot of what's going on. It's a very simple one. And at first you might look at it and think this is trivial, why should I care about this architecture? But actually, in light of the manifold hypothesis, maybe you'll see that there's more to it than you might have thought. This is what's called an autoencoder. You feed an image. So you have this 3 dimension of colors, say, to the left to right, and then you have the 2D thing. And then through operation that is done in the neural network, so in this case it would be convolution, but I'm going to say they're kind of like transformation, projection onto lower dimensional space. Let's call it that. It's not super precise, but let's do that. You go and you project all of that through a low-dimensional space that is called a latent space, and in this you will learn a latent representation, a low-dimensional representation of the data set. Then you just project it back, unfold it all the way back to the original size, and then you train it to reproduce the input. Why would you do that? Because the goal is for it to be good at compressing the information in a low-dimensional space. So learn the latent manifold. And then you really do the difference of 2 dimensions and say, oh, this is very different, just bad. Go back and adjust your weight until you learn like a number of representations that are low dimensional of the images you feed, okay? Much of deep learning and large language model as well in some other sense is actually that, learning low dimensional representation of the rich data set that we can find in the world, okay? So it relates to dimensional reduction principles. You would use PCA or things like this. It relates to information compression. All of this is kind of different views on the same problem, if you will. So what has happened in the last decade maybe, is that self-supervised learning, so that's a specific way of using a data set that's not labeled to actually train a deep learning model, has opened up the possibility of learning representation at Ethernet scales. That's a quick summary in one sentence of what has happened as a key development. And so I told you already natural language might be seen as that as well. The other thing I'd say is that if you go back to LLM, they learn their representation via this next word prediction. They are asked actually to predict the next token, which is essentially a next word. And so a lot of people summarize this as like, this is dumb. It's just a dumb task of learning the next word. But it turns out that out of learning to do that prediction well, they learn many representations, some that are quite useful, that is well beyond, you can argue, and there are demonstrations just telling you what the next word is. And so you should not focus too much on that task. It's dumb, actually. There's a lot of things you can learn from just doing that task. I'm just not going to say more on that, but that's something I put out there so that you have in mind. Of course, there is no guarantee that the representation that you learn are all good, perfect, interesting to human, all of this. We'll get to talk about this. But especially they can be flawed. You can have this one, and every human in this room is going to say, oh, this is like a piece of a question mark. So that's how I'm going to fit it. Naturally, we'll see that, okay? But then the AI might learn some twisted one before it learns the one that the human might naturally learn, okay? So we need to keep that in mind. It might learn many representations that are, from our point of view, imperfect, or weird, we don't know. Basically, there's no guarantee of what it learns. It just learns something, and then we have to play with it and use it. So then, I'm going to try to draw parallels to physics. I don't know that people have probably written about this, I just don't know the literature well enough. This is just my, thought process about this. Our physics models have predictive capabilities. All of them actually, some of the measure of the value we put in the physics model is that they can predict. And then we do use heuristics in physics. Sometimes we invoke the Occam's razor, sometimes other things, that we think it pays off to favor simplicity in our model, generality in how much they generalize and can predict to many other things, and maybe sometimes even beauty, that's a term that has been used in physics, beauty of a theory. And so these are sort of heuristics, there is no proof of it, but we do that. I think if you look at the history of physics, a lot of that has been done. And whether you practice it every day, maybe not, but there are these big ideas that are out there, I think, and people have commented on it. There is also the use of Occam's razor in machine learning, and this is very, very precise, more precise in that context, which is that you must limit the number of parameters in the model you learn, otherwise it's going to overfit and generalize poorly. There is actually quite a parallel between the two if you start thinking about it. We have predictive models, they have predictive models, and we want to learn them so that they're simple and they generalize well. That's actually what we do in physics a lot. I mean by that the fundamental laws of physics, you know, the everyday of what you do, maybe not. I don't know that there is a paper I wrote in my career that's really illustrating this principle, but physics in general as an adventure is something like that. And so the question is, aren't physics theories made of predictive low-dimensional representation, or maybe we want to call them idealization? And I'm not sure how far that argument goes. You know, I'm really posing a question here. I have a feeling that there might be something on that, and maybe I'm wrong. But could we look at physics theories as being low-dimensional representation of complex systems? For sure, we do have things like effective theory, renormalization, strange attractors, universality, various things that actually connect to low-dimensional things, or maybe in statistical physics, you know, just reducing about like taking an average over many particles to get to an average quantity. This is reducing dimensionality in some sense, but and so there's some of that. But I think I mean something that's maybe a bit deeper. I don't mean that in something more abstract, which is like even the simple universal laws of gravitation that we came up with, it works wonderfully. We still use it. Isn't that a compact representation of all two-body orbits that are realized in nature? Isn't that a super compact, low-dimensional representation of actually a lot of natural phenomena? And so that's a question. I don't know that people have written about this. I don't know if it's possible to write about it, but it could be that an AI learns something that would be useful in that sense. That's sort of what motivates me. Okay, so that's all I'm going to say about this, and then take it further. So what's driving the race right now, apart from commercial interest, is the fact that the models are becoming more capable, and so. It's well established in the AI community that the progress is a mix of compute, algorithms, and data. So now they're feeding the whole internet, and they're looking for more data if possible. They're also creating synthetic data. There's various things here that are interesting to discuss. I'm not going to say much more. That actually what people have been saying is that the more flops, so this is effective flops. There's a company called Epoch AI, and their job, and they sell the data, is to collect all types of data about AI progress, to map it out. So that's nice, they have nice figures. And they tell you here, training compute flops, publication date, and then they feed a curve here. There might be even things going faster up here. This is sort of the best model as of today. I think it's like a few months old, maybe, that thing. But basically, people are putting flops, and the more flops they put, and more data they put, the better the models are getting. Okay, that's just what I want you to say. And there's even a measure of how much of that is compute, 7 orders of magnitude here, and 4 orders of magnitude of algorithmic progress. And there is expectation that algorithmic progress might actually make a bigger contribution now that they are more capable. So all of this is being discussed at length, and it's happening. Things are getting better. But they are getting better in ways that are interesting to try to quantify. This is the whole business of evaluating these machines, and because they are capable of many, many things, it's actually challenging to evaluate them well. It turns out it's actually really tricky. So I'm just illustrating here that people have also established, for instance, that various scaling laws. This is purely empirical. The more flops you put, you get more out of it. So for instance, there is, as an evaluator data set, a benchmark, one called MMLU, massive, whatever, I forgot the name of it. But the point is that it's pretty much high school to early college level questions with multiple choice questions with 4 answers of everything. You know, astronomy, physics, sociology, business, whatever, everything, okay? And surely enough, the more flops you put in this, it got better. It's actually saturating here. I don't want to emphasize this number, but this is GPT-3. Where is GPT-3? It's like around here, right? So just over a few years, you have gone up a lot and you saturated the benchmark. So we need new benchmarks because these machines are actually doing better and better. Now, the major caveat here is that they are good at knowledge tasks. You know, they hallucinate as well. I'm just going to put the hallucination on the side for all this talk. If you want to ask me about it, I'll tell you. Let's put that on the side. They are good at knowledge. But but this is a very limited way of probing someone's capability. It might work for some students, and actually I use MCQ, but it's a very narrow way of evaluating compared to what you could do. And so I'll tell you about other ways maybe of evaluating functions. Specifically, if you start getting in them tasks that involve more reasoning and planning or long-term things, they actually feel sort of badly at that as of today. So this is where I get to discuss the frontier capabilities. So I'm going to tell you about graduate level knowledge, some coding, and some reasoning. Sort of give you a very small snapshot of everything that's going on, because again, there is a lot going on, but something that you may not have seen. About, I don't know if it's less than a year ago, something like a year ago, certainly not more than 2 years ago, the people in the AI community realized, oh, we need better benchmark because they're just like blowing through all of our benchmarks. So let's go and pay PhD level contractors, putting quite a lot of money into designing 500 over 500 questions in chemistry, biology, and physics, and included astronomy, and design what they consider that you would need a PhD to answer those questions. But again, multiple choice, 4 choices. Okay, so again, it's limited in its scope. But to get to the right answer, you need to go through and calculate some things. Okay, and then you would expect a human who doesn't have a PhD to struggle. Okay, then what these people did is they also hired other PhD level people, either having a PhD, doing the PhD, or already having a PhD in the domain. So it's not like, hiring the best expert in the world, but people who really know about this. And they also hired educated people who are not experts, who don't have a PhD, but have I think, a university diploma. Okay? So this is what the yellow line is 34%. The educated human, oh, I should tell you, when you have 4 choices, if you got random, you get 25%. So the base is 25, it's here, okay? Okay, the educated human get like 9% more, 34%. So these are challenging questions for educated people who are not PhD level in their field, okay? Then you go to you guys, or maybe not, but maybe more PhD, just out of PhD. So maybe you guys, it's just like you go and they do, I think actually corrected for mistakes, because there's some problems that had mistakes. This happens. Designing problem is very time consuming. If you have never taught, I tell you, this is so time consuming. Designing good problems, okay? I think it's more that they do 74% I've seen from the paper, okay? And so, when now I came out, it looked like a really good test because GPT-3, GPT-4 were going about an educated human, okay? But then it got to be blown through quite quickly. Then there was a lull for a few months, and then O1 came out. So GPT-4 is here. O1 it came less than 2 weeks ago, I think, and it blew through this. In physics, it beats the PhD physicist on that specific task, but still, it's quite impressive. Right? And it uses reasoning to actually go through the arguments and then choose which one is the right question. So they have rich graduate level knowledge, I would claim from that, but just knowledge, and when the answers is a set of 4 possible, okay? So I'm not saying they will replace a graduate student, but that's where we are today.
So what's the difference between GPT-4 and GPT-4? Is it the same data or different data?
Oh yeah, so that's interesting. So I could comment on that. Why don't I go through the questions for this? But the base model, GPT-4 base, has been turned into a chatbot, and then they have put a lot of extra molding it, etc., and they got a lot of juice out of it. So the 4 is getting a lot of juice. Actually, there is one distinction as well, is that 4 was trained on audio, images, and text, not just text. And that might contribute to its better performance. But the base setup is the same. It's just that, you see, when you train a foundation model, it just learns everything that is on the internet, okay? And then you need to mold it towards what you want it to be, and you need to get the juice out of it. And then they have, I don't know what they do. This is all secret now. By the way, that's a comment actually. I don't know what they do, it's all secret, but they got a lot of juice out of it, okay? I mean, I think we can trust them that this is a 4-level model and all this. There's no reason why they would not tell you the truth. We are in an unusual situation. There are things that are created that will impact the world, like call it a phenomenon or an entity or whatever you want to call it, these models, right? Or tool, that is not accessible to scientists to study. I mean that computer scientists are complaining about the fact that they cannot look into these things and play with it freely. And the government cannot also access it to see, it's actually a kind of unusual situation we've had where very, very secret things are being done in the labs and they're secret because it's a business, right? So it makes sense. But then we would like as scientists eventually to be able to study, or even now to be able to study what's going on, but we can't. So it's a very unusual situation we're in. So for that reason, I can't tell you exactly what's going on in making you forward superior. I'm just inferring it from what I know.
But isn't that unusual though? I mean, a lot of social media algorithms are not public.
Yeah, no, that's fair.
Yeah.
That's fair. Let's skip that for the questions. Yeah, we can debate about it. Yeah. Okay, so that's this is that, and then I'm going to tell you that I think these things are superhuman at coding. I don't know how many of you use them at coding, and I don't mean they're superhuman at everything at coding, but I do mean on some things they're superhuman. So if you want a code snippet that's like 20 to 30, 40 lines, it will get you out about the right code. It's just unbelievable. And if you tried ChatGPT a year and a half ago and you were not satisfied, now you'd see it's so much better. Okay. So and of course it takes like 10 seconds to do that when it would take you maybe 15 minutes to write that function or whatever. So in that sense, it's superhuman. But the thing that you might not have appreciated if you have not spent the time evaluating these models that I have is that they're even starting to be good at scientific grade coding. What do I mean? I have a prompt here that says basically take the Lorentz dynamical, it's just to illustrate. Take the Lorentz dynamical system, except I want you to make the parameter of the Lorentz system time dependent with an amplitude and a frequency, and I want you to start here on the z-axis, and I want you to find this parameter, the amplitude and the period of the variation that actually minimize the time it takes the system to cross twice the YZ plane. If I give that to a grad student, it will take them a while to write the code that solves this. Okay? Now this is O1 solution, which as far as I can tell is correct. It runs. I haven't checked for sure, whatever, but it used to be that 4 failed on this, and all the other models failed. They basically, with a collaborator, we have a sort of a benchmark or a study of this. And the point of this is you start being able to ask them to code things that have scientific relevance, I guess. And that's on that basis probably that I'm thinking of building an AI research assistant, and eventually then I'll become an AI physicist. Okay, so I'll tell you more about this. So if you have not done this, this is actually very dark here. I don't know if you can see this is better on my screen, but so let's say you have your favorite package that is 10 years old. It's open source on GitHub. It will know how to code with that. And you might ask it for a simulation, and it might make a few mistakes, which is annoying because you have to trace them. But most of the code lines will be correct. That's what we figured out about like a bit less than a year ago. And so it's starting to be almost useful as an assistant level. Okay. So what about building and evaluating an AI physicist? I will tell you, we're not an AI physicist, just far from it. Far in capability, I don't go far in time. That's another question. But we are not too far from the research assistant that does and go do things for you and come back with a report. That's really what I want to, I'm focusing on at the moment, trying to build. So in terms of evaluation, so I'll tell you, there's a lot of things that are good to do on evaluation. In fact, I told you, all of you, when Sarah come out, you could say, oh, that is a nice little project. Can I evaluate the physics in that model, design prompts and all this? So the way we attack this with 200 graduate, graduate students and undergraduate students and my collaborator, Mohamed Ali here, is to go beyond knowledge and actually try to reproduce what would be an actual scientific experiment. And so we build a dynamic environment, and the LLM is able to probe the environment, ask for an observation, get the observation back, analyze it and say, I want another observations, okay? And it has a budget. You have only 10 observations. And then what the observations are either text output of the location of a two stars in a two-body problem, if you will. That's simulated using a very good astrophysical simulator, okay? And then there is hidden physics in the environment. The AI is told, you know that this is two binary, two stars. Implicitly, that means solar masses, kind of thing, And then find the orbital period, or one of the masses is this. What's the other mass? This sort of hidden physics at this simple level. And then we also have complicated ones. We put the drag coefficient. So the orbit is taking. Find the drag coefficient. It's a Keplerian orbit, but there's drag. Find the drag coefficient from asking to observe. So in some sense, we're after the early days of astronomy, which is people looked at the sky, they mapped out the motion, and from those motion and selecting when to observe and all this, we infer basically universal law of gravitation, right? It's basically a simulation of that in an environment to see whether LLM can do that, which would be sort of an early success if they could. And we have two versions. One is you get the coordinates. So we help you get the coordinates. We have two versions. You get all the coordinates that you ask for in one bunch. Actually, we don't ask you to select when you observe. You get like 20 observations that are nicely sampled. But like you get X, Y on the plane. Or you actually have to schedule your own observations, which involves planning. Which involves, for instance, if you have an eccentric orbit, you should be smart to actually sample a lot around perihelion because it's going fast there. And all of the LLM know about perihelion going fast and approximation going slow, right? But can they use that knowledge to actually solve the problem? And then, so you sample, you basically have a strategy for sampling the observation. And then we have another one where actually we show them images. So dots, with scales, so that they have to read the coordinates and themselves actually infer. So it's a visual version of the benchmark. It's still being finalized. And the result is that prior to O1, because we cannot run O1 through that yet, it's not available with enough of, anyway, we can right now, but it's going to be eventually. The models actually do quite poorly on planning the observations and reasoning on, and then actually following up and effectively helping themselves solve the problem. But if you feed them all of the observations, especially in tabular data, they have surprised us in some ways how they solve the problem. So it's sort of the boundary of the knowledge we can evaluate from that benchmark. There is no such benchmark like this that exists almost, right? It's like, and to be honest, if I were to get, so we have 150 columns, if I were to get my undergraduate students, like, maybe this is second to third year undergraduate level in astronomy, they would take, I don't know how many weeks to go through this. It's actually quite time consuming, but you can get it through in just half an hour, now, and the AI solved it. So now it does a pro job. I don't know how well the undergraduate students do, because I don't evaluate them that way. I evaluate them with multiple choice question or a problem. I don't ask them to redo what Tycho Brahe and Kepler did. So I don't know how well they would do. And so that'd be interesting. I think they would struggle actually possibly. Because there's a lot more to it than actually just having the knowledge, right? Okay, so let me show some example of what will come out. This is a models, GPT-4 mini, a small version, the full version of all, Claude 3.5 Sonnet, which is sort of the best in number of measures. It's actually a little better than 4.0 in a number of measures. And then nowadays O1, so I don't know what O1 will do on this. We give them Python. They love coding to solve, they get better by using Python to solve your problem because they can't do math, but they can code, and the code does the math for them, and they're much better that way. So this is one of the reasons I do everything I do with AI is through coding, because they're so much more capable that way, okay? So they fail, this succeeds. It gets the eccentricity of this ellipse, which is just doing it. So, and because there is code, we can see what the machine is trying to do. The interpretability is key here. So we can see its reasoning to some extent. What is it trying to do, and does it make sense or not? And so in that case, this one is exactly the eccentricity we had. Just perfect answer. So you can fit, and you can realize I should fit the ellipse. Then you think about how to fit the ellipse, and then you implement the code, and it fits the ellipse correctly. Okay. Another one that surprised us. This is r to the minus 2.2 gravity law. We don't tell it what 2.2 is. We just tell it it's r minus alpha different than 2. Just find what the gravity law is. That guy found it. I wouldn't have expected that. We have some traces, so then we get so much data that's generated in codes that just analyzing that is mind-boggling. We actually are designing code to analyze the output from these machines because we have too much data. The data set is 1 million tokens, so it's 1 million words. You just don't go as a human and check everything. It's just impossible. This is an interesting topic I can expand on. But the point is that I would not have expected the machine to be able, because why not? Because it's out of distribution. There is very few examples of this this is not the real world. R minus 2.2 is not the real world. So it has to extrapolate to actually a modified law of gravity and be able to go out of the boundaries of its training. This is actually significant. And he was able to do that, okay? So that's interesting, one of the best, one second. We also have examples of that guy, 3.5 sonnet, going through and then going to numbers that it doesn't make sense. Let me try another method. And he goes and he tries. And eventually, after 3 times, he finds the right answer. This I didn't expect either. So there's things that are interesting that are happening, but as soon as we tell them, plan the observation yourself, they fail miserably. Yeah.
Do you have noise in your data set?
We don't have noise. This is V1. We're going to add a lot of things, but we do a first version that's like super clean, face on, so everything is much simpler than the real world. Yeah. And we're going to add realism to the simulation as we go on.
So yeah, on the center to your point, you said it tried several times. So kind of realize that it failed, right? Or you said
yes,
it failed.
it looks like that. Yeah. When you get an XSD, let's say that. Okay, so this one is a good one. GPT-4 is done on this one. Sorry, it is delay. Because look, fit the eccentricity. Eccentricity is a number between 0 and 1. If you ask for, I am sure we'll tell you it's 0, actually it's between 0 and 1. And it submits 24 million or whatever, So that's dumb. But sometimes we have seen evidence of self-correction, yes. So, I guess the thing you should take from this is that soon you guys, all of us, will be needed to evaluate these machines. Because the people at OpenAI or all this or Google or whatever, there might be some physicists there. But I don't think they have the way of thinking that we have about what is a good testing problems and all this, right? And then this is a simple one. There will be more challenging one to create, right? So benchmarking this thing, creating evaluation is a very interesting way of entering that business if you're interested, okay? I'll just leave that. Okay, how about building an AI research assistant? So this is the early days. I'm hoping that actually maybe at the end of this year, I might have something that a prototype or whatever is probably going to be limited, but that's sort of where I am right now. What we did in that paper that's almost a year old now is that we wanted to evaluate how well it could simulate, to code physics simulation code. So we had things like, so we told it, use this package, which is an open source package, so Rebound for N-body dynamics. And then I had some problem as well with Daedalus. I don't know if you guys know Daedalus. It's a super flexible PDE solver in any type of PDE, any dimension. It's very powerful, but actually it's hard to code and make it work. It's pretty challenging to use. And then we had so there's things like, to give you an example. Calculate the maximum allowed sun energy axis of Io for its surface volcanic activity to persist as a function of Io's mean density. I mean, this is a challenging problem, right? I have things here like, a diffusion problem. How do you need to change the diffusion coefficient to actually, for the initial condition, the peak to decrease by that much or whatever, give me a full code. So there's a simpler version of the problem, more advanced version. But I would say, okay, the thing we did that we created this problem from scratch because that thing has seen everything on the internet. So if you design a benchmark, it needs to be entirely new. Otherwise, it's useless. You don't know what they know from the training, okay? So we designed 50 problems like this. They are scientific code, and the way we did it is that I could ask that problem to a grad student passing an exam, final exam, or maybe take-home exam, if I had taught them, scientific computing using one of those packages. That's sort of the mindset we had. And they failed, so GPT-4 a year ago failed, but on average 80% of the code lines were correct. They were about the right code. And then it would make stupid mistakes like units or having an infinite loop, not thinking about steady state, checking conversion for steady state, things that are kind of obvious, like more undergraduate level thing. But you know what? We never write about those. This is tacit knowledge that's not on the internet. So then the idea that if you can put that knowledge in those machines, then maybe they can do this actually and become assistant, right? So that's pretty much where I am. There's more to it. The other thing is that we have had some tests on O1, this new reasoning model, and it's close to solving well some of these problems. So it's definitely better. And that O1 thing fixed one of my problems. He told me, yeah, it's good, I'll do it, but it's in post. Look at this. And he was correct. It actually figured out that one of my problems that I didn't check was in post. So that actually blew my mind. So there's capabilities that are really interesting out there. That's what I'm saying. It's worth playing with them. And it's very time consuming. So you have to choose to just get into this. But there is things that are happening that are non-trivial. That's what I would say. And in case you think going to an AI physicist is crazy, which is a totally sane view, I think. Let me show you what came out months ago. That guy is a lead, is a senior author on this, and he's my collaborator on a specific benchmark for that we have been funded by a philanthropy called Open Philanthropy to figure out, when is it that the AI will be able to do some science. So kind of what I'm trying to build, and sometimes building a benchmark for that. And then it's a bunch of, it's like a computational chemist, computational biologist. I'm the computational physicist with a number of postdocs here who have joined. And then he's a computational AI person. And so we hope, and there will be human trials. So PhD people will actually be given problems trying to solve, and then you compare to what the human can do. We don't know. At the moment, I think they'll fail. But the question is, can we detect when they start actually doing science like we would do? And this came out in August, and what this is a pipeline or a system that's built on top of this Claude 3.5 Sonnet and GPT-4, and it actually goes and try to create new ideas and checks whether in semantic scholar has this been done already? Oh no, okay, so like just find new ideas to address that problem, and then he proposes an idea. Then he's self-critic. Is that idea good? No. Okay. Then when he finds a good idea after 50 iterations, he said, okay, then you run the experiment. Then he writes a code to run the experiment. Run the experiment, it fails, it's modified, okay, you've looked. Then when the experiment is finished, he just writes a paper. And I have looked at that thing, I have looked at one paper on a topic that I know, and I would say, not bad. It's like maybe a graduate student kind of paper, you know? They also have a data set from acceptance and rejection to their, you know, in a computer science, they have these big conferences. It's organized by conferences. And then they have data set on which paper get accepted or not, because it's all open review, all open, so it's really great. And so they train a model to evaluate whether a paper would be accepted or not. And the best papers from the machine would be accepted in the conferences, according to their classifier. So this demonstrated as a proof of principle that automating science is about becoming possible in AI. I can tell you for reasons, you know, maybe at lunch or whatever, why it doesn't work for physics right now. But it's not crazy. At least in my mind, it's not crazy, because there is a demonstration here in the field of AI that you can automate some of what we do as scientists. This surprised me. I think it surprised many people, because you get a lot of things to put in mind that it would kind of work. No, it's not. There are flaws. There are big flaws in the same way the code that these things write for me for computation physics, there are big flaws. But it's not bad. It's not too far off. Okay, the last point I want to make here is that why would you want to do that? Maybe because you can learn something from the AI. And I will show you a proof of principle that came from Google DeepMind. It's a paper that I really like because it sort of illustrates what we might be hoping for. I think I put the archive number. Yeah, you can check it out. Just like, you know, not even a year old. AlphaZero beats all the humans at chess. Okay? Now it's a narrow capability. Plus, we have a tendency to think it's all about combination of moves. You can all count them. But actually, AlphaZero has learned strategies. You know? And so what they decided is they said, could it be that we can extract some of the representation learned by AlphaZero, specifically elements of strategies? Can we extract those representations from the model, teach them to grandmaster, chess grandmaster, then evaluate the grandmaster on hard problems, on a hard exercise, and have them learn from the AI? And the answer is yes. So they have 4 grandmasters. They started on those problems and they only got, solve those problems maybe on some amount of time. You'd have to, it's a very technical paper and I don't remember all the details of the experiment, but basically they did that, they scored that after 2 phases of learning from what those people were able to extract as representation of why the machine was doing this in this situation. And teaching that to the human grandmasters, they did a lot better. It follows that we could have an AI physicist that does many things we don't understand, but if you can extract what he does, some of that we physicists could learn from it. Okay, that's my conclusion. I leave it to you. I mean, a lot of this is extrapolation, but I'm convinced that some of that could be actually useful eventually. And then the way of thinking of these people, which I think is, I like that way, is that there is a human's representation space. So this is the low-dimensional manifold I was telling you about. Everything we represent in the world and what we do is that the machine learns representation, and some of them, they are beyond our reach, it doesn't make sense to us. But there is maybe some intersection, and that's what they try to find. Something that's close to what the human do, so that it's learnable by the human experts, and they succeeded in a human trial with a chess grandmaster. So I think this is super exciting, because it says, well, maybe there is a path actually to do better science that way. I'm almost done. Can you, yeah? Actually, no. Go.
Do you have any idea how they pulled out the part of the representation that the humans could have?
Very technical. Read the paper and see what, yeah. So I think it's difficult, it's very interesting. I have not digested it yet, because not because I'm interested, I just don't have the time. There's so much going on that I need to pick my battles. But this gives me hope, something like this can be done. My way of doing this is through code. Because code is very, if I ask a machine to code simulations, I can follow rather easily what it's trying to do. Because code is action. And I can infer intent in code, right? So that's my approach to this. What they do, they actually look in the neurons and extract representation in some fancy way. It's challenging. No question is challenging, but at least it's doable. At least that's a proof of principle.
But
Yeah.
don't you say, when you say you code this, you show how the AI should think about this problem?
I'm not sure. Can you rephrase your question? I'm not sure.
When you say code this, it tries to mimic how a human would think about this problem, how a human would code about this problem, because coding is only possible in human ways. You can't code in any alien way, this code wouldn't make sense.
Okay, so can you keep that question for after? I finish and we talk about this various instances. Yeah, it's a good point, but I just want to expand on it, and so I just finish in 2 slides and then we can go to that. Okay, the last thing I want to say, that there are connections to AI safety here. AI safety, in my opinion, is going to become a big thing. So you hear about all the, wow, we're going to all die to various other things. I'm just going to try to highlight here the relevance to us scientists, and maybe you can think about this, whether it makes sense or not. So science is dual use. That's a term from, I don't know where the dual use, but like that's a government term or military term or whatever. Basically, with science you can do good or you can do bad. And there is a problem for us, for the people building the machines. So now I'm include myself, if you will, even though I'm not building much anything at the moment, but like, I'm trying to. Is that we don't know how to align, what's called alignment, but let's think of it as controlling an AI so that it does things in a safe way. And the reason we can't do that is because science is by definition out of distribution. Everything you guys do in this room, essentially nobody has ever written about it or thought about it before, so there is no training data to do it safely. So when you think about training an AI for safety, science is an extra challenge because you work at the limit of human knowledge, by definition. So that's a challenge with science-capable AI. I chose to go with a computational physics agents because I can put them in a sandbox on a computer. They can simulate everything, including nuclear bomb explosions, which actually is a way the governments are improving on their design of nuclear bombs these days. They don't detonate them and test them, right? So there's things you can do. You need to base it on data, but like there are things you can do that way. And so there's no immediate risk to the world. So I think doing it on the computer that way is one approach that provides some more safety. And at the moment, it looks ridiculous to think something dangerous could come out of these machines, but eventually it might. So thinking about how to have a process for that is actually worth So this is going more to your point, we can go back to that, but I think having human understandable code facilitates a lot the interpretability. I mentioned that, and I think that's a key aspect here, to try to understand what's going on with the AI way of doing things. This is going to be super important when we get agents. Everybody's trying to build these agents, things that work autonomously. So I can tell you from the benchmark we have, we get so many traces of machines doing things that it's very time consuming to figure out what is it that it's trying to do. And we'll have that if AI agents become a thing, we'll have that at a society scale. Just monitoring this to make sure things are going the way we want is going to be quite challenging. We need to invent techniques to do that efficiently. And the other thing that I'm sort of pursuing, which is a more abstract point, but you might want to think about it as well, or I'm just bringing that to your attention, is that physics provides an ultimate ground truth. AI can tell you things, can be convincing, you've heard about this, and they can be convincing. And we are all subject to those biases and things that make us believe or not, all of us, including us scientists, right? And so it gets really tricky when they get really smart to deal with that. And to some extent, the objective reality, as long as our instruments stay passive instruments, they're not things that are AI things, but we have our passive instruments, basically physics is an ultimate ground truth. You cannot fool us on physics because that's a world. And so there is some element of this that is maybe physics is a good, especially good testing ground for what these machines are doing and how they justify their decisions and their actions and all this. It's a bit of an abstract concept, but there is something to it. And so I could discuss more about this more detail if you want. So I'll stop here. I don't know how much time there is, but I'll just say that, sort of, and somewhat optimistic view on the current AGI progress suggests that building an AI physicist may be possible, and that we could learn from it, from its AI representations. And then that any science-capable AI poses interesting, unique risks to safety, and those are our responsibility. That's it. So maybe you can go back to your question. Yeah.
So my question is actually related with this. You showed a figure where two circles, and you said AI can think sometimes out of the box where humans can think.
Yeah.
But in your prompt, you are saying that the AI should write a code. And you are limiting that AI to just only do kind of an analysis, which would be when these two circles are touching each other. So you are limiting the information. So in that case, how much do you think you are testing the AI? Because you're not using the full functionality of AI.
Yeah, I think that's true. I actually do think that I agree with that there are some capabilities that we don't know of in these machines. That is very true. But what I would say that I'm not really limiting it so much. If it invents a novel algorithm, a novel way of approaching the problem I give it, it can show it to me in code, and I can learn from that. That will be my answer. There are other things that it might be doing that I don't know about. So I'm not saying it's a fully interpretable solution, but that's one of the best ones I know of as a scientist. Yeah, so it's not perfect, but there's an avenue to address the issue. Yeah.
Why is GPT-4o performing so bad compared to Claude in your specific experiment? I mean, what does the code tell us?
I actually don't have a model-to-model comparisons. Well, Nolan is leading that analysis, and what is coming out is that the machine makes stupid mistakes like n=1 for a star, assuming it is a one solar mass star, and not even checking that the units are m-sun in the code. Like things that are really ridiculous. This is actually the most common answer, assuming that a star has a one solar mass. And that's because it's not thinking through that, sure, this is the most common thing you find on the internet, but that's not what you should assume here. Okay, so this can be fixed, yeah. We don't have comparison one-on-one. I don't know what to answer. I don't know that we'll pursue that because I'm not sure that's the best thing. I think just sort of, we don't know how they train. We don't know, the datasets are different, the training methods, so we could just have evidence that one does that better than the other, but what does that mean? I think more like the general strokes of it's failed, so units, they're really bad at units, it's incredible. Given how smart they are on other things. So this is the sort of general thing we're after, because they can be addressed.
So you should teach it to use AstroPi.
Yeah, correct. Yeah, so actually my colleague tried. Mohammed, he tried, and he was through an iteration, and he went to 20 prompts for a machine to solve a problem. But the prompt had so much in it that actually it was turned into a human prompt engineering exercise and not a machine exercise. Yeah. So at least I was with GPT-4 Turbo like a year ago. Yeah.
You've been talking about evaluating whether this AI physicist is doing good physics. What about using AI to evaluate the work of human physicists? Like, will the peer review process have a code reviewing AI soon?
I think that's possible, yeah. I think, yeah, why not? I think it's going to be hard to get some of the things that we have in our head. We have a lot of context in our head, and these machines can do well if you provide them with a lot of context. But I don't think they can get the whole context that a physicist expert in their field has right now. So there might be limitation there. But there are actually attempts at building an automated peer review. And to some extent, the AI scientist has actually a sub-pipeline that is that. For AI, a peer reviewer that has been trained on actually humans deciding what is a good paper for this AI conference and what is a bad paper. Okay, so you could think of building these pipelines. And I think they might start being used. At this point, the machines are good enough that they might be helpful. I probably want a human to check. But like to sort out quickly your submissions, that might be possible, yeah.
We have a question, hand up online. So Falk.
Yes, hello. Thank you for this very nice talk. It's very, very interesting. A lot of us are also teaching as professors, of course, and I wonder what your opinion is on how does the extrapolation, maybe 1, 2, 3 years down the road of where this could be going, and you have outlined that. What do you think does this mean for what and how we need to teach the students, maybe both at the undergrad and also at the graduate level? How do we teach them? What will change when we teach?
Yeah, that's a great question. I'm worried about getting what I'm going to say on record. But I'll just say one sentence. It's not clear to me that the current university business model is going to keep working. By that I mean how we get funded, why the students come to learn at university, and all this. I think there might be a challenge, and I worry about it. Yeah, I'm just going to say that. And how we teach is part of that. It's like you get asked, what is the skills you need when you go in the workforce? Do we teach them? We still don't want to actually go through the hard learning, because we're trying to teach them hard academic learning things to get a diploma when maybe what's needed outside is different, it's changing so fast. I think there is a number of challenges there that I see them as real. I mean, they don't materialize today, but they might in a few years. So it's not a very positive view I have.
I just like clarification, example which I advocated with AI physics. Are you saying that we only facilitate some of the requirements of physics, or are you saying something different? Now, what I mean by something different is this. Let's take what you said about AlphaZero. AlphaZero did not, although he beat a master, did not come up with any groundbreaking original tactic and strategies in chess. Now, once the quantized gravity, given the fact that every physicist failed quantized gravity, it seems like the groundbreaking original ideas, in essence, creativity. And thus far, the computers have not put any door of creativity or true groundbreaking original ideas. So are you saying that AI physics will facilitate to some level, or are you advocating
Yeah.
major breakthroughs?
Yeah, I'll tell you what I think.
Creativity and groundbreaking ideas.
So, AlphaGo, so I'm going to answer on the side first and then directly. AlphaGo has actually come up with a move 37, that all the expert Go players in the world is like, what is this? And they learn from it. So maybe you don't like AlphaZero, but there is a demonstration with AlphaGo of something that, a strategy that people learned and had not thought about. If you don't think a machine can be creative, I highly recommend you read the AI Scientist paper, where they say, the authors were saying, wow, there were so many interesting ideas that came out of that ideation process. And my own experimentation with trying to just combine two different topics and just come up with ideas suggests that, there is a limited things we have in our human brain. These things have all of human knowledge. Sure, they make mistakes and but actually, I think there is a case to be made that they might be good at ideation. That's my view.
think with that, let's thank our speaker again.